Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
So this would essentially be the free body diagram for the system. W in this case just means weight. So we know that the weight of the child is 140 newtons, which means that the mass of the child would be equal to 140 newtons divided by the acceleration due to gravity, so 9.8 meters per second squared. And we're getting the mass of the child equaling 14.3 kilograms. We're going to say that W sub x would simply be equal to mg sine of theta, and W sub y would be mg cosine of theta. So given this, for part A, we can say that we're going to direct the x-axis up the incline. So A, the acceleration would be negative 0.86 meters per second squared, because up the incline would be positive. So Newton's second law would essentially be equal to the force of friction, kinetic, or we can say, rather, we can simply reference a diagram and say frictional force kinetic minus 140 sine of 25 degrees would equal m, the mass of the child, times negative 0.86. And at this point, we can solve and say that F sub k would be equal to approximately 47 newtons. Now, we can also apply Newton's second law to the y-axis and say that the force normal would minus 140, and here it would be cosine of 25 degrees. This would equal 0 because the child has translational equilibrium in the y direction, and we can say that the force normal then equals approximately 127 newtons. Now, if we wanted to find the coefficient of kinetic friction, we know that the coefficient of kinetic friction would then be equal to the kinetic frictional force divided by force normal. So this would be 47 divided by 127. And we find a coefficient of kinetic friction of 0.37. So that would be your answer for part A. Now, we're going to return to our first equation in part A, and we see that if the downhill component of the weight force was insufficient to overcome the static friction, this means that the child would not slide at all. So we can say that we would require, this would be the condition for the child to not slide, 140 sine of 25 degrees would have to be greater than the maximum static frictional force. And this would be equal to the coefficient of static friction times the force normal. So this means that here, tangent of 25 degrees would simply be equal to 0.47, and this would be equal to the coefficient of static friction. Therefore, the coefficient of static friction this would be order for child not to slide down. Now, notice that the coefficient of static friction is a bit greater than the coefficient of kinetic friction. Of course, that is to be expected. And if the coefficient of kinetic friction would never exceed the coefficient of static friction, because then, of course, it wouldn't, the child would not move. So here, however, the minimum value of the coefficient of static friction equals the coefficient of kinetic friction, and we can say that, again, if the coefficient of kinetic friction exceeded the coefficient of static friction, then when the static friction were to overcome then it would start to move. However, this is impossible because then the coefficient of kinetic friction would be large enough to cause the deceleration. So therefore, here, there are bounds on the coefficient of static friction. Therefore, 0.47 greater than the coefficient of static friction, greater than 0.37. Anything greater, this means that it would be causing deceleration, and we don't want it to move. So here, this would be the true answer, again, for child to not move. That would be your answer for part B. That is the end of the solution. Thank you for watching.